All right, here we are. This is Chapter 8, Problem Set 1. Question number 1 says, in the figure, a block is moving horizontally. It can take 3 frictionless routes, differing only in elevation, to reach the dashed line. Rank the routes according to the speed of the block and the travel time to the finish line greatest first. I think one easy way to view this is if we think about it in the conservation of energy. So I'll use some pie charts. I'll draw pie charts for each of these. And ostensibly, within my ability to draw these, all the pie charts should be the same size because the energy is conserved. So when you're doing this, one thing you need to know is, well, first of all, let's do some colors. So let's use this blue as the kinetic energy, and then we'll use this green here as the gravitational potential energy. Now, one thing we can do is we can say, well, where's our zero height? Because knowing where your zero height is important to understanding how much potential energy you have. So let's say our zero height is here. So that means that there's no gravitational potential energy here, but there is here and up here. So what's going on in the first one? Let's say that this first one here, it's moving to the right, and let's say that half of it is gravitational potential energy and half of it is kinetic energy. And as it slides this way, it doesn't get any faster, doesn't go up or down any hills, and so we're going to say that the energy stays the same for this guy. But what's going on for, let's say, this one down here? If you look at this one down here and you say, oh, well, this is the zero height, therefore there's no gravitational potential energy. That means all the energy is kinetic. And then what's happening at this one up here? All right, it went up. If it goes up the same height, I mean, frankly, to be honest, if it goes up the same height, you would convert all of it to gravitational potential. But let's say it's almost, we don't know its exact same height, so we'll just say it's mostly gravitational potential. And here you have the largest amount of kinetic energy, here you have a medium amount, and here you have a small amount. And since you have large kinetic energy, you have large speed, medium speed, and small speed. You could just think about it too, is if you go up the hill, you're probably going slower. So, what about the time? Well, one of the ideas that we're familiar with is that since the distance traveled is equal to the speed times the time. And we think about this as an average speed, so I'll put the bar over the top, which means average here, right? We could think about the average speed here, and what I notice is that since this has the largest average speed, as speed goes up, a bigger speed would result in a smaller time. And a smaller speed would result in a bigger time. So there's an inverse relationship between speed and time. So since this was going the slowest, it would take the biggest amount of time, a medium amount of time, and a small amount of time. Let's look at question 5. Question 5 says, a block slides from A to C along a frictionless ramp, and then it passes through horizontal regions C to D where a frictional force acts on it. If the block's kinetic energy, is the block's kinetic energy increasing, decreasing, or constant in region A to B, and then B to C, and then C to D? So let's do that first. So again, what we can do is we can draw some pie charts to help us understand what's going on. So again, if I apply the conservation of energy, the pies are the same size everywhere we go. So let's make our zero height down here. Now, we do that because when the block is here, it's going to have, right, it's not going to have any gravitational potential energy. So up here, this is the highest. So it's going to have the most gravitational potential energy. And the least amount of kinetic energy. Down here, it's all kinetic energy. Here, let's say, I don't know, it's up above here, but it's not quite as high as that, so and then, so here, this is also frictionless, which means that and then what happened here is that as it slid across this rough surface from C to D here, right, some thermal energy was generated and released to the surroundings. And so, what does that mean? It means we have some thermal energy generated. The red is the thermal energy. So, the question is, what happens in each region? So between A and B, the kinetic energy increased. Between B and C, the kinetic energy decreased. And between C and D, the kinetic energy decreased. And you could just see that by the pie charts. What about the total mechanical energy? Well, here, first of all, we're going to use E. We're going to make that be the mechanical energy. And the mechanical energy consists of gravitational potential, kinetic, and elastic potential. And so here, E is constant. Here, E is constant. What happens here? E is decreasing because this thermal energy that's generated is released to the surroundings. It's not conserved within the Earth block system. And so we could say that you're generating some thermal energy. It's not the mechanical energy. It's released to the surroundings. 9. Okay? In order to do 9, we're definitely going to need some more pie charts. So let's put these on here and see what they look like. Let me do a quick edit. I want to do 2 pie charts per. I want to do before and after, before and after, before and after. So all right, so here's the deal. All of them are at the same height, and they're all moving the same speed. Therefore, they have some amount of gravitational energy and some amount of kinetic energy. So because I know that this one's going to slide down, so we have to somehow say that my zero height is somewhere down here. So they all start with some gravitational potential energy. So we don't know the proportions, but let's just make it easier for us. And let's say that they all start with half gravitational, half potential. Oh, half gravitational potential, half kinetic. And each of these is slowing to a stop, which means they're not going to have any more kinetic energy when we're done. But they all start with the same amount of gravitational potential because they're all at the same height. So for the second, or for the first one, it doesn't change its height, so therefore the amount of gravitational potential doesn't change, which means all the kinetic energy all went to the thermal energy that was generated. This second one, though, it's going to go down the ramp and eventually come to a stop, which means that its gravitational potential energy is decreasing. Again, it's still losing all the kinetic energy. And we're just going to be left with the thermal energy. And this last one, it's going to go up the hill before it comes to a stop, which means it's gaining some gravitational potential energy. And again, it comes to a stop, and all the rest of the energy is converted to thermal energy. And so, number 9, the question is, rank the situations according to the increase in thermal energy greatest first. Well, if you look, this one gained the most thermal energy, then this one a little less, and this one the least amount. All right. Problem 7. Problem 7 says, in figure, it shows a thin rod of 2 meters long and negligible mass that can pivot about one end and rotate in a vertical circle. The ball of mass m, 5 kilograms, attached to the other end. The rod is pulled aside 30 degrees and released with initial velocity v0 as the ball descends to its lowest point. How much work does the gravitational force do on it, and what is the change in the gravitational potential energy? All right, let's just do those first. So this problem is challenging because the geometry is not obvious. So when I'm looking at this, okay, I'm going to call this down here, we're going to call that my 0 height. And where the ball starts is right here. And so it's going to go from here to here, which is fine. But look at what's going on in this right here. This all of a sudden becomes a small geometry problem, because if you notice this length is 2 meters right there. All right, we're going to call that L. What that means is this right here is also, oh, that's not L, I'm just kidding. The whole thing from here to here is L. So if you call this the H, this is the height difference from the beginning to the end here. What that means is that this section right here, from here to here, I'm going to call that L minus H. And if I look at this triangle, this right triangle now, here's my angle 30 degrees. This L minus H is the adjacent side, and this L is the hypotenuse. So what I have here is I can make a cosine statement. So the cosine of my angle is equal to the adjacent side. If I multiply both sides by L, so I'm going to solve for H. And if I factor an L out of both of those terms, I have L times 1 minus cosine theta. So why do I care about L at all? Well, if I want to know the work done by the gravitational force, I need to take the force times the distance that are parallel. The the gravitational force is mg, and that's in the down direction. And I need the distance that's in the down direction, which is this height right here. And luckily for us, these are in the same direction, so I can just calculate it by mgh, which is equal to 5 times the gravitational field strength was at 10. And can we solve for h here? This is 2 times 1 minus the cosine of 30. I don't know where my calculator is. So you calculate this out, and it turns out h is equal to 0.27. So the work done by the gravitational force is 13.4 joules. Part B says, what is the change in gravitational potential energy? Well, this is one of our concepts that we kind of need to pay attention to, but it's not super obvious, is that the work done by the gravitational force or gravitational field is equal to the opposite of the energy stored. Now, you could write this as the other way. You could write it as the change in the potential energy is equal to the negative work. And the reason is that the work was positive and the potential energy is decreasing. Therefore, they have to have the opposite sign, okay? Because the work was positive, the energy was decreasing. That's how you know they have the opposite sign. So what that tells you is the change in the gravitational potential energy would be equal to negative 13.4 joules. C says, if the gravitational potential energy is taken to be 0 at its lowest point, what is the value of the ball when it was released? All right, so it's saying, like, let's call this down here, h is equal to 0. So if I just do the change, our idea of change is going to be, oh no, sorry, typo. Final minus initial. So what it's saying is we want this to be equal to 0. So let this go to 0. That means the change is equal to the final. Oh, that's a total lie. That's not what it's saying. Actually, it's the final that's 0. That was weird. So if the change is equal to negative 13.4 is equal to negative UG initial, then UG initial is equal to 13.4 joules. This isn't actually that surprising because if we say this is 0 and this is the original, the initial, well, it has to be equal to the work that was done. D says, do the magnitudes of these answers increase, decrease, or remain the same if theta is increased? Well, if I were to increase my theta here, release this from, let's say, a higher angle, maybe all the way out here, then the mg would stay the same, but the height would increase. Height increases, work increases, everything else increases. So if theta goes up, everything increases. And that is it for Chapter 8, problem set 1.